Good day, everybody. This is Wednesday, the 11th of March, and we're here to talk on a special SDO session from the Metaverse Standards Forum. Today's title is Geospatial Standards to Address the Requirements of Real-World Use Cases. I am Leonard Daly, one of the session organizers, along with Thomas Stockhammer. And as of late yesterday, we had 33 registrations, so we'll see a bunch more people coming in. So during the session, please mute yourself. It does help to change your name to your Zoom name to your company, calling your name, but please don't use your company, your name. It does help us just track who's here and also for the participants to know who's actually speaking. We will have a Q&A session later on where you'll be welcome to speak. This meeting is open for everyone. Everything presented here is considered public information. The forum is not a standards development organization or SDO, and we must remain in compliance with antitrust and competition laws. So there's no discussion of detailed specification, designs, patents, pricings, or litigation. This meeting is recorded and will be published on our YouTube channel. Links will be pushed out later on, primarily in chat. The slide deck will be available with the video recording. The links to this will also be available from the Metaverse Standards Foundation's forum's website. So during the course of the session today, please keep all discussions professional, friendly, and civil. The forum does have a code of conduct, which you can find on our website. As I mentioned earlier, there will be a Q&A session after the presentations. So we are using Zoom chat to collect the questions. You're welcome to write the questions in there. We're also working with Discord to be able to continue conversations both during the session and afterwards. And if you have something that you feel is too difficult or too complex to actually put into writing, raise your hand during the Q&A portion and you will be called upon. So MSF creates a complete suite of spatial web standards, not just about 3D, but also about privacy, payments, identity, reputation, IP ownership, networking, geolocation, and even robotic-oriented spatial computing. And it'll take hundreds of standards from dozens of standards organizations. So this is not a small problem. We are not trying to solve it by ourselves. So we are a nonprofit organization. It's attracted over 2,600 organizational members across the world to assist and accelerate the development of the needed standards with wide industry input and visibility. The forum undertakes pre- and post-standardization activities, including use case generation, draft specification, feedback, and identification of standardization and standard gaps and opportunities for standard organizations to leverage and align each other's work. Post-standardization efforts include testing, interoperability, and creating tooling and educational materials. MSF is pragmatic and driven by bottom-up industry priorities to help solve today's most acute interoperability pain points. We have tried to avoid to define the metaverse or create metaverse roadmaps as it continues to evolve in a manner that no one is able to predict at this time. So a couple terminologies here, and these terminologies are mostly to help us in MSF and others when we talk about it to understand the various pieces. They're not meant to be as hard definitions, and things frequently flow between and across boundaries. So XR is the umbrella term for augmented reality, virtual reality, or mixed reality. It applies to wearable headsets and their controls and usage. Spatial computing is a broader or well-established term that includes XR sensors to understand the user and their environment, including using AI to recognize gestures for speech and intuitive user interaction. Then the metaverse brings all this together, is the result of connecting multiple spatial computing experiences and users, including integrating them into the real world. Our view is that there will be a single metaverse We just don't know what exactly that looks like, but it will take multiple platforms to make it work. So how will things evolve? And in the diagram, the left side shows how things evolve from the base internet, or even before the DARPANET times, to what we currently believe see and understand as our primary 2D web through the browsers. The spatial web will have a similar sort of evolution. It's just it will be much faster, not necessarily computing wise, but the evolution will be faster. But it fundamentally is based on standards, just like the 2D web. XR adoption has been increasing, and I believe for this audience that you are well aware of this. It's really just beginning to take off in the consumer market. It has been around in the enterprise for quite a while. The VR market is very socially isolating in that you put on a headset and you're pretty much not aware of anything else that happens around you, which, given some of the recent happenings, may not be such a bad thing, but it does very much limit what you see, hear, and interact with. So we're just on the frontier of the consumer AR taking off and becoming a major player and major driver in what happens in the entire market. This shows all the interactions between various pieces of XR, spatial computing, and AI. It's a very interconnected diagram, and it by no means is going to claim that it captures everything going on, but it does get to the real points of information that has to travel between these three major pieces of AIs, XRs, and spatial computing. So the metaverse, as we've been hitting on the last several slides, is at the intersection of XR, AI, and spatial computing. AI is really important for understanding and providing context to people, and also the computing of what happens as a person experiences things or how the person interacts with things. Spatial computing just brings everything together and allows users to interact with each other. So MSF was constructed truly from the bottom up, with multiple ideas forming the basis for 15 working groups. This is a chart not meant to be read, but just sort of uh, absorbed, in that there's a whole lot of working groups attacking a large number of technical issues. This just got to be too complex to manage and presented a very confusing public interface. So last year, the MSF undertook an effort to consolidate from 15 down to 5 without losing any of the technical activities. So these 5 groups on the left form the basis for holding all of the technical activities. This is still currently work in progress. Roughly about 50% of the consolidation has been completed, and we expect the rest of it to be completed in the next couple of months. We are always looking for people to participate, whether you wish to be a participating member, which is free, a principal member, which does have a cost associated with your organizational size, or a volunteer. We especially like and appreciate volunteers. If you are interested, please contact us at the URLs listed there. And if you have any ideas on how the organization can better interact with SDOs, standard development organizations, or the public for educational information or anything else, please do contact us. So this is number 7 of the Forum SDO special sessions. The other 6 are listed under previous sessions. Currently, we do not have a session scheduled. The next session is not yet scheduled. If you want to suggest a topic, either as a presenter or just saying, this is what I would like to hear about, there's a forum there, and we'll have links to the forum posted up later. And as mentioned before, we will have a Q&A session. It will be live and recorded. Also, after the fact, or even during the session, you can join our Discord at this QR code and participate. You can either ask questions in Discord or Zoom, and they will get answered live. So onto the presentation. There are three presenters today. Scott Simmons is the OpenGeo Consortium Chief Standards Officer. He's responsible for cross SDO coordination. And I should point out that I personally have known these people for decades. Scott's running it about 20 years. Steve Smith has been a spatial computing architect for mobile, is a currently spatial computing architect for mobile GIS. He has worked a lot of previous jobs, including commercial pilot, oceanographic research scientist, has been involved in a tremendous amount of standards, including DIS and ANSI SQL, IEEE, DIS, ISO work, and OGC Simple Features, Open Location Services, CityGML, and GeoPose. And he's currently chair of Metaverse Standard Forum's Real Virtual Worlds Integration Group, OGC GeoPose Group, and the OGC CityGML Group. Mike McCann, I've known for almost 30 years, is a senior software engineer at Monterey Bay Aquarium Research Institute, also known as MBARI. He's a member of the board of directors of the Web3D Consortium and co-chair of its Geospatial Working Group. So I'd like to welcome Scott to lead off the presentations and with the presentation on OGC.
Great. Thank you very much, Leonard. And let me get my slides shared here. Fantastic. Thank you very much for the introduction, Leonard. And I'm really pleased to see so many people here. I recognize a lot of names in the chat and some others that I don't. So that's fantastic. So my name again is Scott Simmons. I look after the standardization activities in the Open Geospatial Consortium. And today, Steve Smith and I are going to present to you 4 standards, plus a little bit of background, focused very much on data models. So when Leonard put up a slide about the 2D and 3D webs, he talked about the scene understanding and semantics. And that's really what we want to talk about today. These are the fundamental standards that underlie the information you might experience when working in a metaverse environment. There's a reason why we partition these. And so we'll get into that. First, just really briefly about OGC, who we are, Open Geospatial Consortium. We're dedicated to ensuring that any kind of location information, any geospatial information, is exchangeable, understandable, and that those data are accessible. And so we work against the FAIR principles, making information findable, accessible, interoperable, and reusable. And we do that through the development of standards, applied research and development, and convening in a number of meetings and other forums. We have membership from commercial, government, and research arms, more than 500 members total around the world. Last I checked, I think we have members in all but 2 inhabited time zones in the world. So it's great global representation. Membership right now is about 40% commercial and 30 each government and research and academia. And so that also gives us a good cross-section of the entirety of the geospatial marketplace, as well as related industries. So we work, I noted in the sort of the highlight of my bio that later read out that, I've worked with cross SDO standardization activities because there are other affiliated bodies that cover topics that we're interested in. And so we have members, some cases, in common. And so for digital twins and such, we work with Building Smart International and others to ensure that we're aligning our respective work efforts. So today, you're going to see us present, as I noted, 4 data models. And why all these data models? Why do we need 4 data models to talk about geospatial? And I'm going to tell you, there's a whole lot more than 4 out there. I'm just going to, we're going to highlight 4 right now. So for those of you who do not come from the spatial realm, there is an example we use time and time again. Those who come from the geospatial world, oh my God, you've seen these slides or something like them 1,000 times, and I apologize. But for others, this may help you understand. And that's the example of a lighthouse. You think of a lighthouse as a tall structure, probably on the coast, has some characteristics that we can all imagine. Fine, we just described it as we see it, but there is an underlying data model. How is that lighthouse expressed and used in various contexts? And so from the lighthouse keeper's perspective, this gentleman here lives in that lighthouse and he also works there. And so for him, it's a residence and a place of work. And he probably knows about the staircase and some things he has to do with generators and changing bulbs and whatever else you might do at a lighthouse keeper. But that is really a residence and a place of work from his perspective. For a postal delivery person, it's an address. It's a place where you drop some mail off. So that lighthouse is an addressable structure. What it looks like, how big it is probably really unimportant. So long as that person can get to the mailbox, that's all they care about. And so when they need to deliver the mail, they need to understand where does it fit in their route and how is it characterized? Do you have to walk up to it? Can you drive up to it, etc.? So understanding the context in which that delivery person operates helps describe in the data model how the actual lighthouse is represented. If you're on a container ship, that's a beautiful drawing. It is a navigational aid. So the container ship hopefully has not quite touched those rocks yet because the lighthouse was hopefully turned on. But the idea is that it sees a light emerging at a height, and it has a navigation chart in the bridge of that ship that shows where the light should be in 3 dimensions and the angle and color of its beam. So the structure, the building itself is utterly unimportant unless it's daylight and you're using it to sort of triangulate. But at nighttime, when you're navigating, there are certain characteristics about the light emerging from the lighthouse that are really important to that navigator. And finally, if you're a pilot, the lighthouse is what they call a vertical obstruction. The lighthouse is tall enough that you could fly into it. And so understanding where it is and how tall it is very important. Its actual structure, construction, and purpose is literally unimportant. The pilot just does not want to fly into it. So this single building, the single structure that we can all imagine, has multiple representations. And for each one of those representations I just described, there are existing data models to describe them in those contexts. And those data models ideally interoperate so that if you're working from one data model, you can traverse to another and understand your same object, your same geospatial feature in a different context. And this is really important, again, when we talk about in the metaverse, looking at the semantics of the information, how we interact with those objects we see, those objects we're working with in our frame. What do they tell us? How might we depict them? And how can we use those in analysis against other objects? So if you look at OGC and our standards suite, and we have over 150 standards, so we've been busy for the last 32 years, you'll see that we specialize data models for these various purposes. And if you look at our standards portfolio on the right, again, you see lots and lots of standards, and there's different types. We have standards for sensors, we have standards that get the information to the user via APIs, cataloging, et cetera. But in the middle in blue, we have a whole pile of data models. And those data models describe the world, the natural and built world, from various perspectives. They're highly specialized for a reason. You need experts to describe these things properly. So we need to focus those descriptions. You also need the contextual information of some aspect of your environment. We'll take water as an example, surface water. A river flows into a lake or the ocean. It flows in a river flows in one direction, downhill. Understanding those dynamics and the relationships. And if you think of the network of water, where something is going to flow from one body of water to another, that is very, very specialized. It's a description of something that is also a body of water that you cross with a bridge that from the bridge builder's perspective is just so wide and so deep, but it has very specific context in the water perspective. And so if you take all these standards and we look at this example of the real world, you can see we have a whole pile of different ways to describe the various things here. You've got CityGML to describe the buildings itself. We have something called land infra that talks about the infrastructure, the roads, the railroads, et cetera. Pipeline ML to talk about pipelines, be they underground or above ground. GeoSciML, that's a science standard for describing the three-dimensional geology. Water ML, I just described the concept of having rivers, lakes, flows, et cetera, all in standards. And MUDDI, the model for underground data definition that we'll talk about a little bit later today as well, to talk about that underground infrastructure and where it lies in context. All of these standards interoperate. They're intended, they're built under common rules. They have common encoding patterns beneath them. And ideally, one of those standards can be used to feed another in certain circumstances. And I'll bring this up when we talk a little bit later about something called IndoorGML. So CityGML that Steve will talk about talks about that infrastructure, but how do you navigate the indoors part of it? So that's sort of the introduction to what we're going to talk about. I have here for you 4 topics. Steve's going to talk about GeoPose and CityGML, and then I'll jump back in and tell you about MUDDI and IndoorGML. And so with that, I'd like to pass it on to Steve.
CityGML and GeoPose are two OGC standards. CityGML is in its third version. The work really started pretty close to the beginning of that 32 years that Scott was talking about. GeoPose is about 5 years old and it's evolving. I'm going to be a little bit nonlinear in the exploration of these two standards so that you'll end up with some links to information and examples and data and software that you can go into in whatever detail makes sense if you're interested in more specific or just more detailed information. So CityGML, I would say it goes a little bit beyond what Scott said as far as just describing buildings. CityGML aims with about 10 different thematic modules. By that I mean modules which have semantic models for different kinds of things. So buildings is one of those things. Actually, more generally, stuff that people build or constructions is the most general module, and then buildings are a specialization of that. There's also water and tunnel and bridges and roads and vegetation and what we call furniture, which are things like signs and trash bins and other things that are kind of not so individually interesting, but the fact that they're planted around the environment is important. And so these are what I call complete models, which means that if you turn these models into a virtual reality and you virtually wandered around in these spaces, that you would find surfaces to support you so you wouldn't fall through a crack into nowhere, for example. You'd find doors and windows that open and all sorts of things that are normal human activities, whether on your own feet or in a vehicle. CityGML now has hundreds of millions. And we'll look at a GitHub repo in a minute where they keep a count of how many open access models are available. And today's count is 213 million. If you don't count the global level, where there's, I think, 2.7 billion buildings modeled. The name CityGML is a little bit misleading then. And I've talked a little bit about the one misleading aspect is it's really environmental models tuned to the semantics, to the human conception of the built environment. So it's stuff that humans create and plant outdoors in the world. And these models originally, the specification back in the days when XML was bright, shiny, and new, originally defined and expressed in GML, which is an XML sublanguage for geographic data, and it's very highly developed within OGC. So GML or XML is still commonly used, but it's not required, and there are ports to JSON, SQL, and Java, among others. There's dozens, actually, but these are the important ones. one key aspect of these models is that, again, every single component, so there are identifiable pieces within these models that have identifiers, and each one has a semantic class that fits into this 10 module categorization of the things which, in addition, have geometry. And one of the really exciting things that's happened in the last 3 or 4 years is that there have been efforts to look at a purely semantic version of the CityGML model by extracting the standards machine readable definition written in UML into an ontology that's encoded in OWL. So that's CityGML, models of the built environment. GeoPose is a different kind of standard. It's actually very specific, somewhat mathematical concept which has been expressed in a way that makes it easy to exchange a certain kind of information. And that information is information about reference frames. So if you're familiar with reference frames, that totally makes sense. If you're not, just think of picking a coordinate system to do some calculations or some presentation or navigation. That selection of the coordinate system, so what are the coordinates? How are they oriented in space? What's their relationship to maybe some more globally defined coordinate system? That reference frame is the framework within which you do these problems. And so I'm going to go in a little bit, it will seem in circles in talking about GeoPose because in a way that's its origin. So the concept of pose is familiar from computer graphics, where it's the data it would describe to explain where a camera or light is and the direction it's pointing. So in 3 dimensions, there's 3 values, 3 degrees of freedom that go with position, and then there are 3 rotations to orient a pose, and those are the other 3 degrees of freedom in what people refer to as the 6th degree of freedom model. And this goes actually pretty deeply into the way human brains are wired. The way we conceive of space and orientation in space is pretty well encapsulated by the idea of the mathematical concepts of the special Euclidean group 3-dimensional and the rotational group SO3, which describes the rotations. So a pose is where you put a camera or a light and how that camera or light is pointing. Well, this actually is the same information that you need to define a reference frame. So we started out with some requests from outside of OGC for a data object which would contain these 6 pieces of information that describe a pose and some way to link them to geographic coordinate reference systems. So you might think of the WGS84 system that GPS devices report, for example, or UTM, or any kind of map projection, excuse me, that that part is the geo in GeoPose, and the reason that this came to OGC for standardization is exactly this geo part of the GeoPose. We completed version 1 in 2023. We're working on enhancements now with version 1.1, which is completely backwards compatible, but the main difference is that conceptually it starts with reference frame and it works toward a GeoPose as a serialization format rather than starting with GeoPose and then explaining how it fits into a context which includes reference frames. Part of what OGC does to enhance the standards and test them and refine them before and after they're actually approved as standards is to run test beds where actual experiments are run, usually with things moving around, and able to create interesting videos. And in 2023, we participated in testbed 19 and really extended the kinds of spaces to more or less anything from the pseudo-Riemannian curved space-time of general relativity down to the simple-minded Newtonian, Galilean, Euclidean space that human brains work well with. The CityGML standard consists of a conceptual model and an exchange format. The conceptual model is really a combination of a geometric model and a semantic model. The applications of this are partly in planning or mostly in planning and archiving aspects of the built environment. And of course, buildings are a key feature in this. Some countries have chosen to put part of their national geological and infrastructure into CityGML form or form derived from CityGML. Some countries are modeling more or less all of their buildings in CityGML. Applications and use cases involve visualization, of course, and navigation, autonomous vehicles, and a really important one is energy calculations. So, for example, solar potential or heat loss, also radio propagation, anything really where there is some activity that involves either navigating or moving through a built environment or propagating some signal or moving something through a built environment, or the archive and cataloging aspect of simply keeping track of where are the buildings, where are the entrances, where are the windows. That's it. So CityGML has a resource link, which is here in the slide. Afterwards, I'll put these in the chat as well. You can also go to citygml.org and you end up in the same place. So I'm going to take a little walk through this landing page here. The standards are available here. And data files that are needed if you're going to actually do, for example, extraction of the semantic model. The one most interesting to me anyway, link, so there's a lot of links there and they're more or less self-explanatory, but the awesome CityGML GitHub repo is pretty amazing. And this is the one where it's a collection of the open CityGML data that's available. You can see in the listing here, it's a little tiny, maybe 21 countries, 66 different regions or cities, 215 million buildings. These are all open source, freely available, and the links to get to them are in this awesome CityGML website. If we look at the country list here, take a look at Germany. So like there's complete Bavaria. Let's look at, so I'm picking this at random. I haven't pre-checked it's going to look good, but I think it will. These are all using cesium as the so this gives you idea of what the level of detail in Tokyo is. Anyway, lots of 66 country or 66 areas, 21 countries, lots of data, a lot of different levels of detail. CityGML has 4 specific levels of detail, which are a little different from the levels of detail you might experience in a game engine, where more or less those are automatically coarsening and finer resolution depending on the resolution from your viewpoint on your screen. And these levels of detail have to do with the modeling rules to create the model itself. So the 2.7 billion building global collection is all done in level of detail 1. Level of detail 1 is extruded building footprint raised up to either an AI guessed height of the building or a recorded height of the building. So that's CityGML 3. CityGML 3 has been stable for about 5 years. There's a huge amount of data that's been put into CityGML 3 form, and there is a lot, again, of model construction. There's almost no change to the standard except for bug fixes, and those have been very infrequent the last year or two. So GeoPose 1.0. So we started with a requirement that we would end up with a JSON encoded position orientation. This came from the augmented reality and machine vision communities. And again, we then related this to reference frames and reference frame transformations. But we were really focused on the result that we knew we wanted to get. So in some ways, it's a good way to focus and produce a standard that's directly useful to the community that wants to use it. In another more reflective time in my head anyway, it seems that starting with the first or nearly first principles and working toward the artifact is more logical. And that's what we're doing now. We've rewriting the conceptual model, separating it from the JSON encoding, so it looks like other OGC standards, and taking into account the work in OGC testbed 19, where we extended the GeoPose to work in non-Euclidean space. So it's really quite general in what's possible. And it might seem crazy to want to go beyond sort of what works for Newton and Galileo, but many actual practical spatial computing tasks, especially ones that have to do with spacecraft in the sort of near to mid Earth orbit distances out to maybe geosynchronous orbit height, that actually, if you think about the GPS satellites, gravity, the acceleration of gravity is about a quarter of what it is on the surface of the Earth, which means that the clocks seem to run faster. And then they're moving in such a way that makes the clocks seem to run slower. So you have both general relativistic effects and spatial relativistic effects. So what's a GeoPose? Again, GeoPose is just in one sentence, 6 numbers to describe where a camera is and how it's oriented. The geo part comes from tying it to a geographic reference frame. And there's always in this kind of description an outer reference frame, which is the definition of it is just made up by people. So it's fixed and given, and it's an environment within which then you can create local sub-reference frames that link back to the outer frame. And this connection between this outer frame, which is defined by maybe a national mapping agency, is the geo. GeoPose itself is just a standard data model that expresses the 6 degrees of freedom for position orientation. We picked as a native local coordinate system one that is tangent to the surface and compatible with, I'll just say it that way, the WGS84 model of the Earth that's used for GPS and a lot of other things. So the resources at geopose.org, again, as in the case of CityGML, you can find whatever sort of resources you're interested in. Number of companies have implemented or contributed. And then there is a GitHub repo with code and data. sandbox where you can actually test your programming requirements and concepts against a built-in environment that will support you, and the reviewer's guide, which kind of guides you through what GeoPose standard has. So again, we took a very pragmatic approach to producing GeoPose 1.0, focusing on the JSON encoded 6 degrees of freedom of position and orientation attached to this local tangent plane. So it's like up is up and north is north and east is east, just like it works in your head. Now we are going back and reversing the order of the concepts in the conceptual model so that we start with the most general idea of spaces and reference frames and then produce the GeoPose as an artifact. One of the important things that's a connection with Metaverse Standards Forum is that in the real virtual worlds integration group, which is now part of spatial computing, we have a project where we are benchmarking different approaches to visual positioning. So visual positioning is you provide an image and something tells you where that image is and or where the device was that sensed it was and which way it was pointed. In other words, a pose. And we're adding requirements came from that group in MSF to OGC, and the GeoPose Standards Working Group in OGC is supporting the requirements of the MSF group by producing some new visual positioning support. So again, visual positioning takes a 2D visual image and turns it into a GeoPose. It's analogous to what a human does by walking around an environment and building up a mental model of what's there. So again, in summary, an image goes in and a GeoPose comes out. So it could be a camera, it could be some other sort of imaging device, but it goes through a pipeline where things happen to the image, and what pops out at the far end is a position orientation. This illustrates one common way to do it, which is to build up a point cloud from many image observations and then match new images against that point cloud. There are other approaches as well. So we look at briefly some good example of this point cloud matching, where again, we're going from an image to a GeoPose.
And it has no notion of the globe.
This is Gavorosaurus from
On the right side,
Nokia Bell Labs. And he's talking about the process. And the thing to notice is that poses and GeoPoses and geo things pop up all through this, and this is where we're providing the support.
No drift and unlimited processing resources, but they are relatively slow to use for localization. And combining the two is done in the following way. So the mobile device periodically sends certain keyframes or some other localization data to this localization server, and the server tries to align the map, the image with the map, and then returns the transformation that brings the image into the global coordinate frame. And if this is known to the mobile device, then the mobile device can reorient its local coordinate frame to be matching the global one. I mentioned that on the right side, this is usually a point cloud, but it can be some other method. You can even these days train a neural network to do localization. So there are plenty of methods, but the general architecture is like this. And on the left side, we have many different VIO engines. AR Core and AR Kit, they are the ones built into the mobile operating systems. There are also other ones, a Finnish company called Spectacular AI, for example, that is offered for robot, but there are plenty of others. And on the right side, Google, Apple, Meta, Niantic, Microsoft, they all offer visual positioning systems, but unfortunately they are proprietary and not compatible with each other. Also some startups, for example, Augmented and Immersal. But again, these are not compatible with each other. It would be so nice to have a standardized protocol here in the middle, so that any mobile device can talk to any of the visual localization services, because all these are somehow limited to locations that were mapped by the respective companies. And it's hard if you're a developer or an end user, if you want to map your own space, you are basically stuck. Because just an example, Google cannot enter your apartment for map, so you have to do it yourself somehow. So our idea was in the OpenAI Cloud for a long time, and also in this MSF forum, to create something that is open and can be modified by anyone and can be hosted by anyone. Luckily, this year we won some funding for this, and we developed this inside Nokia and release it in the OpenAI Cloud GitHub repos. The overall architecture is relatively simple. So we have three components. There is a map builder component, which takes in the images from a recorder app, and it builds a feature point cloud map.
Okay, so Gabor there has made the pitch for the protocol sitting in the middle of his diagram, supporting the visual positioning systems, and that's part of the new work in the OGC GeoPose SWIG. They're planned for GeoPose 1.3, and target is to finish that in 2026. Gabor mentioned that there are other ways to do the matching. One of the ones that we're comparing in MSF, which also uses the same support, is to use Gaussian spots, so radiance field modeling, and matching against that instead of a point cloud. We provide position uncertainty information and pointing uncertainty information along with the GeoPose. So image goes in, GeoPose comes out, but it's a GeoPose with some quality information that tells you how much you can rely on both the three numbers that tell you the position and the three numbers that tell you the orientation. So that's it for me on OGC GeoPose and OGC CityGML.
Thank you very much, Steve. The next presenter, Scott, has a little bit more to add to all this, so we'll turn it over to him.
Thanks, Steve. So, as Steve indicated, CityGML and GeoPose, these are really the two most critical for us to talk about today. But I'm going put forward just a little more information on two additional standards, MUDDI and IndoorGML. We didn't pick these four standards at random. Rather, we picked standards for which there's a compelling reason to work with these in a metaverse or XR concept. And I think you'll see that, and I'll highlight that for both of these. So starting with MUDDI. MUDDI is a model for underground data definition and integration, and it's trying to solve a problem that underground infrastructure data, as we understand it now, is very poorly documented, very poorly located, and we really don't understand relationships between different elements underground. Storage of the information, be it the geometry, be it its characteristics, its semantics, all highly variable. And then you can imagine why that is. If you have a company that provides water services, sewer services, you have someone else doing electricity, someone else doing gas, they all have their own structured information that describes their work the way it needs to be depicted. And those aren't all common, and those aren't necessarily integratable. And what you end up with is something that looks like this. I mean, the real underground is super, super messy. And if you don't know where any of this stuff is, it's really, really hard to do excavation. One of the major factors driving GeoPose was, in fact, the cost to excavate and the cost to repair all the stuff you bust when you excavate. I'm sure every single one of us has lost water or power due to excavations gone wrong. No negative intent. No one had a purpose to make it inconvenient for you. It's just the way things work. And so to develop this data, we went through a number of use cases. On the data side, it's how can we prevent these kinds of problems, be they disasters, be they just inconveniences, via working in the underground environment. On the data visualization perspective, the driving use case really was an AR type use case. So someone's construction engineer is walking down the street, has to plan an excavation, and if they can, on some device, see in an augmented fashion that infrastructure beneath their feet, they can better understand maybe where to position equipment, where to start the work, etc. So somebody really, from day one, was driven by these use cases. And we had some good foundations to go on. Super ugly things like this, what as-built maps really look like. After you install your infrastructure, you're supposed to tell people where you put it. There is a standard for describing that information. We leverage that as input to MUDDI, understanding that the depiction may not be accurate, but at least it's a good starting place. And so with that, we developed a data model. We have a conceptual data model that is MUDDI itself. It considers various references, be that linear referencing standards, spatial depiction, how things look in 2 and 3D, the underground data information, as I just showed on the previous slide, and collects that so that the variety of underground infrastructure elements and the context in which they lie, that is the geology or the hydrogeology or the backfill, et cetera, are all depicted in a common fashion, and you can understand where everything sits, where it's related to each other, where it's related to the underlying conditions. And then from that, the community can build their own logical and physical data models so they can actually develop the implementations against MUDDI. And I'll talk about one of those in a moment. In a super simple fashion, this is what's in MUDDI. You have some areas that describe where you're working. You have your networks and the description of all the elements of those networks. You talk about how they're connected. There's the environment, so the soil, groundwater, bedrock, et cetera. Other accessories, how do you access those, manholes, et cetera. And then finally, you have all the attribution for all these elements, all networked, all understood, and all depicted in 3 dimensions. There are also provisions for accuracy assessments, so you can depict something in a 3-dimensional orientation along with the information that states this is plus or minus 16 centimeters or whatever other parameters you might have, so people understand an envelope of uncertainty around your underground information. Perhaps the best use case right now and the most comprehensive information set is the UK's National Underground Asset Register. This is a depiction of the entirety of the underground infrastructure of the entire UK, excluding Northern Ireland, I believe, at this point, and parts of Scotland. It's not complete, but under significant work run by the UK's Geospatial Commission with a lot of leverage of UK Ordnance Survey. And that is an attempt to have a unified underground infrastructure depiction of the entirety of the country, recognizing that there are hundreds and hundreds of controlling entities of all that information. And so, of course, there's all sorts of politics and policies about how you integrate this, but it's been a very successful project and is being now modeled in other cities and other regions of the world as a means to describe the underground infrastructure. We just had a workshop a couple months ago with a nation of Bahrain to model the entirety of Bahrain's underground infrastructure in great detail, and we know a number of other nations are doing the same. The next one I want to talk about is IndoorGML. So just like underground, indoor is also a complex problem. With CityGML, we can model our underground infrastructure, but it maybe doesn't give you all the context you need. Similarly, a good detailed 3D building model in CityGML can depict that building, can talk a bit about its function, but there's other characteristics that you might need for indoor use of those spaces that IndoorGML covers. IndoorGML takes as input models such as CityGML, but also building information model in the IFC format, other floor plans, etc. You have editors to create an IndoorGML visualization, and then you push out the results to location-based services, navigation apps, etc. There are two fundamental concepts in IndoorGML. One of those is the concept of spaces. What are the indoor spaces? How do you subdivide those spaces, and what is the connectivity between them? So what is their physical dimension, as well as what are other characteristics of the spaces? Do they have carpet on the floor, etc., so that you understand more about how those spaces can be used. The second, and my favorite part, and since you're on this call right now, you're probably all a bunch of nerds like I am, is this concept of Poincare duality. That is, we have the spaces, but we have a separate geometric representation of the relationships between those spaces. And that relationship can be navigability. So are there doorways between the spaces? Can those doors be traversed by a walking human? Can those doors be traversed by a wheelchair? Is it wide enough? Is it flat enough? Can a robot get through those? Are spaces connected by a stairwell or an elevator? All of that graphic knowledge of how you move inside the space is depicted as a network graph. But you can also depict in the same fashion other information about those spaces. What is the Wi-Fi coverage of your indoor spaces in 3 dimensions? Other factors such as emergency evacuation. Are spaces findable and accessible from the exterior by firefighters? And can people be evacuated, or are there alternative routes out if certain space connections are closed? And so this duality, the secondary network, is really the key, the IndoorGML functionality. And so quite simply, you take a CityGML data set or some other data set, you convert that into a space model, you then add this graph to depict that relationship, and you have an IndoorGML data set. Just last week, OGC held its 134th member meeting, where we discussed all sorts of standards activities, and there was a brand new effort coming out in the IndoorGML SWIG for rapid development of models, as well as pushing them into and extracting them from databases via SQL. And the SQL part maybe is not as interested, but this tooling being developed at Busan National University in Korea allows floor plans to quickly be converted into 3D space models via highly automated means using the Unity rendering engine. And it's really, really impressive work. And so there's some really great, clever new work on the encodings, getting CityGML into alternative encodings like JSON to make it simpler to use, as well as I noted here, the use of SQL to explore these models and more rapidly make calculations against them or queries against them. And some brand new work, literally last week as well, is a high degree of automation now converting industry foundation classes, IFC, the fundamental building information modeling standard, into IndoorGML. And if any of you on the phone call here know how complex IFC is, and its geometric representations do not align well with the traditional geospatial people, it's a very complicated problem to convert IFC into something that we use in a more geospatial sense. But some, again, brilliant work also being done out of Busan National University with some supporting work out of University of New South Wales. So just brilliant stuff going on IndoorGML. So with that, I want to stop talking about our data models. I know we want to leave time for Mike McCann to talk to you and then answer some questions. So thanks for your attention, and I will stop my share.
Thank you very much, Scott. Our next presenter is Mike McCann from the Web3D Consortium.
Hi there. This is Mike McCann. Let me share my screen. I think you should be able to be seeing my first slide. Can I get a yes or no on that?
All good.
Okay. So, so the title of my talk is X3D Geospatial for the 3D web. And it's where spatial data meets interactive 3D visualization. And first to talk a little bit about the Web 3D Consortium. We have over a 30-year legacy of 3D graphics for the web. And our main focus is standards development and shepherding our X3D standard and other standards through the ISO standardization process. So we're very involved in community and collaboration, especially, you know, with other standards development organizations. We have annual conferences. Our next conference is this fall. Hopefully things will be safe for us all to attend. Our hosts are very cognizant of those considerations. So that's October 13th to 15th this year in Doha, Qatar. So the Web3D Consortium is a member-funded, community-driven, nonprofit organization. We develop royalty-free ISO specifications for X3D and human animation. So there's technical expertise that we draw from academia, government, industry, research professionals. Our standards are royalty-free, and they're really focused on interactive 3D graphics for the web. We have several open source implementations, 3 of them currently in development or in continued support fashion is X3DOM, JavaScript library that can load into any web browser, uses WebGL underneath, but provides the declarative format of X3D for scene generation. Xite, modern JavaScript engine, and then Castle game engine for 3D games. So, you know, our motto is, you know, X3D, 3D anywhere. We target mobile, desktop, all browsers, even cave environments. So this rich cross-platform capability that really is used and comes out of more academic and research environments, but it intersects lots of versatile applications in what we call the verticals of the medical field, geospatial, CAD, CAD/CAM, and more. So there are rich 3D features that we can define in a scene, and we can define interaction between those objects in a scene and generate animation. And because it is a standard, the big attractiveness of it is the durability of your workflows that you develop around X3D, that they stand the test of time. It is X3D version. The standard is in active development. We're currently, you know, working on version 4, which is focused on integrating with a lot of the other standards that are developed around the web, like audio and MPEG, other multimedia capabilities. It intersects with all the neat developments in 3D graphics and GLTF, and we interact with the specialized domains that are really interested in getting their data into a web environment for visualization, so that, you know, we have interactions with other standards groups like DICOM for medical imagery, STEP for CAD/CAM objects and models, of course, OGC for geospatial, and there's other domain-specific standards organizations. So over the history of Web3D, it has its roots in the VRML, virtual reality modeling language, back in the late 90s. And as time has grown, you know, gone on, we have grown by adopting, integrating with, using other standards that have come along the way. And this is a graphic showing, you know, that evolution of X3D. And then if you look in the right-hand side of this graph in 2026. We're integrating, support HTML5, GLTF, WebXR, and now 3D tiles, OGC 3D tiles. So the general workflow for someone who wants to use X3D is they would think about creating a scene graph for what they want to represent. For me, it's going to be oceanographic data, but we have the data coming from all kinds of sources, and there's that convert step where we have good support of exporters from Blender, SketchUp, Unity, 3D Studio Max. Those tools have a lot of exports to X3D or VRML, which is still backward compatible. Then you bring it into those assets into your X3D scene description model, where you can add interaction with audio and video or behavior between your 3D elements, and then have it delivered to the user on whatever device they want to view the data on. So the last step is to publish on the web. So I'm going to talk a bit about the geospatial component in X3D. So X3D is a declarative 3D graphics standard. You're not actually writing the actual commands to draw triangles and polygons, but you're instead saying, I have this terrain, or I have this object and I want to place it at this location. And I don't expect you to read all the bullets here, since the geospatial component is part of X3D, which is a rich standard that supports all kinds of different domains and graphics capabilities. What we wanted to do with the geospatial component was add the accuracy and the understanding of models of the Earth, and then provide the capability to do the messy coordinate transformations between a 3D graphics Cartesian coordinate system and, say, latitude, longitude, and elevation or depth from a WGS 84 ellipsoid. So the geospatial component handles all that math, the convert between the two, and then understands things like how do we place something on the globe. And the lower right of this plot has just kind of a sampling of the different nodes that form the scene graph in an X3D scene. So for instance, a geo-elevation grid, a very simple representation of a grid for how you want the terrain to look. We have a viewpoint for a geographic camera position and orientation inside a scene. And then a fundamental node in geospatial is the geocoordinate, which is just like an X3D coordinate. You can build any kind of geometry out of geocoordinates, which have a concept of a place on the globe. So now on to our current development, or new development for us, is the integration of OGC 3D tiles inside X3D. And we recently, just last August, awarded a grant from the Cesium Ecosystem Grant Program. And I'm just going to read the sentence here from this, is taken from the Cesium website. This project expands the 3D tiles ecosystem by creating a pipeline to stream massive 3D geospatial content using X3DOM and X3D-based browser for visualization of Interactive 3D in the web. The end result will provide an efficient way to store and transmit 3D data in a tiled format using X3DOM, allowing for the visualization of large-scale 3D scenes in real time. This work will bring synergy and interoperability to two popular but disconnected international open geospatial standards, X3D and 3D tiles. The project will be managed by the Web3D Consortium in partnership with its members, Earthstruck, Virginia Tech, MBARI, and Versar. So just one more bit about how X3D and OGC 3D tiles is really a collaboration, and I think we're using the standards as they were intended to be used, and applying it for the for the domains in which X3D finds a home, and for me that's in oceanographic data. And if I have time, I can later share some personal experiences with our activities at MBARI to use the 3D web for displaying our data. Yeah, maybe I'll save those if we have a Q&A, but I'd just like to end my presentation here with a video from the MBARI YouTube channel, which is quite popular for its display of weird animals that we find in the ocean. So, but we also have videos like this one, which showcases our engineering progress and capabilities. So there are some flashing lights in this video, so just be warned about that. So I'll let this play.
Just off the coast from MBARI, countless mysteries await below the surface. One of them is named Sur Ridge. Sur Ridge stands over 500 meters tall and stretches over 20 kilometers long, roughly the size of Manhattan. MBARI is working to create maps of Sur Ridge to better understand this unique ecosystem. Ship-based sonars map large areas at 25-meter resolution and are good for navigation. Mapping at 1-meter resolution, autonomous underwater vehicles flying just 50 meters above the seafloor allow researchers to target areas of interest. In 2013, MBARI and NOAA scientists discovered an underwater oasis at Sur Ridge. At 5-centimeter resolution, you can clearly see the complex rock outcrops that create essential coral and sponge habitats. To study this hotspot, we needed to get even closer. So MBARI engineers built a mapping tool sled and mounted it on our remotely operated vehicle, Doc Ricketts. The mapping tool sled is equipped with LiDAR, multi-beam sonar, stereo cameras, and strobe lights. The ROV carefully flies so that these sensors are always just 3 meters from the bottom. The sensors are mounted on a rotating frame so that they point directly at the surface they're surveying, even as the ROV traverses up and down rugged cliffs. Together, the sonar and LiDAR reveal the location and size of delicate deep-sea corals, sponges, and other animals on the sea floor. At 1-centimeter resolution, ROV surveys are simply breathtaking. Bubblegum corals, like this one, can be hundreds of years old and as big as a king-sized mattress. These amazing images demonstrate what's possible when scientists and engineers work together to develop new technology for exploring the deep ocean.
Okay, so just that video was made about a decade ago, and now we've got a lot of these kind of data from the low altitude survey system, and much of it sits in our data archive and files in which a person has to be an expert to be able to look at it and use it, create maps and so forth. So it's been my desire here at MBARI to take all the data that we collect and make it much more easily accessible and viewable, not only by the scientists, but even the general public. And for that, it's like, well, we've got this web, we've got, just incredible 3D graphics capabilities. Why is it so hard to merge them all together? And I think it was at a SIGGRAPH meeting many years ago, a few decades ago, where at a working group, I presented, kind of this, our use case here at MBARI for that. So why can't we merge this really nice 3D graphics capability with all the rich data that we're able to collect? And a big part of that is using standards for how we create our data, save it, archive it, and then make it available. So that's been an ongoing effort for that, and we found that X3D is that kind of generalized format, which really does intersect with the 3D graphics capability, and it's targeted for the web, which is our main presentation method for our data. So, and at that time, 20 some years ago, there were globe viewers that were coming out like Google Earth and Worldwind and so forth. And I said, well, I've got subsurface data. I got data below the surface of the earth, and a lot of those tools could not display that. And I said, well, we need to do vertical exaggeration of the data so we can discern what's happening in the surface of the ocean, where all these plants live and create half of the oxygen that we breathe. That's important to look at. So, and they couldn't do that, but X3D has been there for us, and as we've moved along, it's grown and adopted these standards, and now is X3D tiles, which will provide that rich, very large data set viewing capability. Again, it's my last slide here. There's some links. I'll share the slides with the group, where these links are linkable. And thank you for having us here to talk and share what our standards organization does, and perhaps how we can even interact more. Okay, thanks.
Thank you very much, Mike. And now while we get three presenters on and turn on their cameras, I want to go over a couple things for the Q&A. You are welcome to put them in chat, and we've had a couple questions already in there. As we're going through these, you can also raise your hand, and we'll call on you to speak. In between, though, if you can keep yourself muted just to avoid any crosstalk or background noise. But before we get to the Q&A, I'd like you to, at some point today, take this session survey. You can use the QR code on the screen. I also put the link in there. It is a short survey, just a few questions. And the intent here is that we will use the feedback from your comments to improve these sessions, either to make sure that we're talking on the right topics or to improve the actual operation of any one of these sessions. Because this first question is directed to you guys. Specifically, I think this is towards Scott and Mike. The two of you, can you compare and contrast the Web3D Consortium and the OGC approaches to standards development?
Well, I'll talk a little bit just about our approach, and then we can compare and contrast as needed. We in OGC we have sort of the fundamental principles, as probably every standards organization has, about transparency and consensus. And so our process involves developing these standards in dedicated working groups for each standard. So each standard has its own specific working group that has its own intellectual property rights constraints on who's involved. And those experts get together because they can focus the most on the standard. But through that development process, we ultimately go to a membership-wide review of the work. Every piece of work goes out to public comment, so we want public information, solicitation of those ideas. And then finally, our entirety of membership must vote to approve the standard. So the standards working group, the people that really focus on this standard, have to offer a compelling reason why this standard should be part of our community's resources, and convince the remainder of our members that that's really important.
Yeah, Web3D is not too different than that. We're composed of working groups. We have an X3D working group, which is shepherding the standard, and then there's the more domain-specific working groups like geospatial or medical or CAD, and it's ground up. People start with their use cases. There's discussions in the working groups, and for example, now with the 3D tiles, there's open discussion now about, do we need a new node in the collection of nodes that make up X3D to define that this is a 3D tiles inline that we need to bring into the scene. So a lot of it for us in Web3D, we're really interested in practical implementations. So we would test in a development branch on one of the open source browsers like X3DOM or Xsite, and we rely on the maintainers of those code bases to implement the standards that are in discussion, because actual real implementations help inform whether the standard is correct or not.
To Steve and Mike, how do the Web3D and GeoPose concepts agree or conflict?
I can start and make a general statement. There are a lot of different standards that actually have the same concept implemented in different ways. So it boils down to 6 numbers normally, and exactly how they're structured and represented differs. So I think they're conceptually compatible and practically incompatible.
Yeah. I think there's a lot of commonality between GeoPose. You mentioned six degrees of freedom that are represented by those 6 numbers. I think the GeoPose standard is equivalent to the GeoViewpoint node in X3D. And theoretically, they're really the same thing. They use a model for the Earth like WGS84 ellipsoid. There's that conversion to the Cartesian coordinate system that the 3D graphic system uses. The internal coordinate system for X3D Geospatial is the Earth-centered, Earth-fixed coordinate system, or what we call geocentric in X3D. And I think that's the same for GeoPose.
So GeoPose has a basic version, which makes a similar assumption, although our native coordinate system, local coordinate system, is then further rotated to be tangent to the Earth, to the ellipsoid, the WGS84 ellipsoid at the center point. So that we end up with a local coordinate system that has opposite gravity, and north is north and east is east.
Yeah, that's interesting. That's I think a detail that perhaps I missed. And in the geospatial node set, we have a node called GeoTransform, which does that operation, which then rotates the coordinate system to be on that tangent plane at a center point that you define in the scene.
Okay, so it boils down to conceptually probably close to identical, practically incompatible. But that's okay. One of the things that we're trying to do, well, in GeoPose, we actually had 2 ideas and they contradict. So one was, well, we'll just describe the way to represent the 6 degrees of freedom, the 6 numbers, in a way that suits us, and then we'll provide support for converting to the way other communities want to speak. So basically, wrappers to translate to X3D speak, or moving features in OGC is another standard that does the same thing in a different way. And then the other, so that's one idea, was we provide not really as a normative part of a standard, so you don't have to follow any rules, but you have the convenience of having reference software that does the transformation from one way of describing it to another. And then the other was, we should just speak all languages in GeoPose, so we have a fragmented set of representations, which are all logically identical, but cater to the different communication needs of different communities. And we started out with the latter, and I think now we're pretty much agreed that having libraries available is a better approach to fostering this translation capability.
Okay, Scott.
Yeah.
What kind of geospatial models or standards does OGC not yet define? Or what would you personally be what is it, or what else would you be actively working on that you haven't discussed today that's of course appropriate to this topic?
Yeah, when you saw the little diagram I showed, there's a whole pile of encodings out there for a lot of stuff. I'll give an example of one that's in work right now and soon to go out to vote for my membership is something we refer to as emission ML. So how do you describe emission data, gaseous emission data on the Earth in a fashion that it's visual, that you can visualize it and you can also make calculations against it. And so that's a volume metric, but also perhaps a graphical depiction of extent of various emissions above certain thresholds. So there's atmospheric type standards like that that are common. We have a couple of proposals in to work with more biological data. So one is to talk about the location, position, and relative characteristics and sizes and such of trees for use in carbon accounting. So there's lots and lots. There's many parts of our physical world that need to get modeled. Lots of those models maybe already exist. I would say we're probably spending less and less time on specific domains these days and instead developing bridges to other ways to characterize some of those things and just ensure that they're spatially enabled properly. Another example would be with respect to environmental accounting. So not just emissions, but um, indices of other types of pollution or wildlife biodiversity and such. And so there's already great ways to characterize that. There's standards in various communities to provide that information, and we're working more just to spatially enable that under an umbrella of something we refer to as geospatial reporting indicators. So any indicator generically can have a position assigned. So that I would say our focus going forward is going to be more on that generic, let's slap some spatial knowledge onto your already existing good way to describe your problem.
Thank you, Scott. This question is from chat, and I presume it's mostly for Mike. It says, to what extent are we seeing X3D used for creating virtual 3D information spaces as distinct from representations of things in the physical world, if at all?
Can you restate that question again, and then?
Sure. So it's if anybody following along, it's in chat from Mike Bennett at 814. To what extent are we seeing X3D used for creating virtual 3D information spaces as distinct from representations of things in the physical world, if at all?
Okay. So this gets at like information visualization versus like digital twin kind of concept, maybe.
Exactly.
Yeah. Well, it's up to the creativity of the developer, and I've at our conferences I've seen both almost equally, because it X3D is very general in terms of what constructs you can create and what scene you can put together. You know, for me, I'm much more focused on the representations from things in the physical world. So, you know, we have these large databases at MUDDI that just need to be presented, and we'd view X3D as the practical presentation layer for that.
Okay. And remind people that you are free to post questions in chat or raise your hand. And particularly if you did post something in chat that may need clarification, we may ask you to speak or at least help us in chat, whatever you feel comfortable with. Another question, and Mike, I'm not sure if you are the right person or capable of answering this just because of the topic. The question is, how does Web3D relate to Web of Worlds? And if you feel you need to call on somebody, go ahead.
Well, I see Nicholas is on the call here, and he's one of the authors, I think, of the Web of Worlds proposal. But it's, I think, in general, it's about promoting, you know, X3D as a practical standard for implementing a Web of Worlds metadata or metaverse world. And I don't know, Nicholas, if you have anything you want to add.
Well, thanks so much. Well, this is a great session. I really appreciate your all the presentations here, and I do think there's a great alignment in front of us, and this really helps to kind of understand what that might be. I think one of the things about the Web of Worlds that maybe is the quick, 30-second takeaway is that it's a little bit like the OGC approach to less formats, more APIs, right? And when we have model types like X3D or GLTF, where we're pulling things off of a server, that's great, but we have stateful servers now. And so the kind of bits in flight is much more about the experience and the composability of assets rather than about what format they're in. So pulling out these concepts, it is definitely a unification of GeoPose and GLTF and X3D, but it's not really about formats. And I think that's the big takeaway for Web of Worlds. So thank you. Looking forward to talking more. And that group will be putting out a white paper this quarter from their work. So looking forward to sharing that and getting feedback from the group. Over.
All right. Thank you, Nicholas. So we have, for the most part, reached the end of the questions. If I missed a question that you posted to chat, I'm sorry. Please raise your hand and we'll locate it or let you speak it. If not, let's give thanks to our three presenters. Oh, sorry. We have a hand up. Don, go ahead.
Thanks, Leonard. It's in the chat. I followed up also on Mike's excellent question. X3D can be very data driven. It's not hard to write a style sheet or use one of our struggling typed APIs to automatically produce large sets of data. I don't think Mike's staying up late at night recording every polygon from one form to another. So thank you, Mike, for the question, and you're copied on the query on our list, and we'll see some of the latest, greatest, and share that. So thank you.
Thank you. Yeah, I look forward to that.
Don, I didn't understand the second clause in your first sentence.
I'm sorry, was that to me?
It was, yeah. So you say, I can't imagine. See if I can find it again.
Oh, sure. Yeah, we can put things at different places in space and time. Of course, you guys can. And I think it's an open door. Nobody's really converted GeoPose directly into X3D. Let's do that. That's all I was saying in the other chat. And I see the same kind of data being represented in each side in maybe a little different ways, but you guys are experts at transformation. We have some very skilled people too. Let's do it. And I think the motivator is, does this provide an even larger capability for metaverse? That gives us a goal, perhaps Web of Worlds, so if stronger GeoPose is valuable, okay, let's do it. That's what I was trying to communicate, Steve.
Got it. Thanks.
Okay. Thank you. Let's thank our presenters, Scott Simmons, OGC Chief Standards Officer, Steve Smith, Senior Architect, and Mike McCann, Senior Engineer. And thank you, all the attendees, for being here. Please fill out the survey. It is really important to us, and we use it as we go forward and develop new presentations and new sessions. We will stick around for a few minutes if there's any questions that you last minute have, but we're going to conclude the session now. Thank you very much for coming.
Yeah. Thanks, Leonard.
Thanks, Leonard. Thanks, everybody.